Industry 6.0 is the artificial intelligence genie out of the bottle. There is no turning back for this genius. Hypothalamus Artificial Intelligence, HY. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Industry 6.0 has arrived. Are you ready? Most people, including many scientists and experts in artificial intelligence, think that it is limited to generative pre-trained transformers models. In this way, this vision of AI has become popular. HY considers that today artificial intelligence is generative pre-trained transformers and mathematical programming. This is the main theme of HY's research. Alan Turing, a brilliant British mathematician and one of the leading scientific geniuses of the 20th century, is considered the father of modern computing and artificial intelligence. In October 1950, Alan Turing proposed a test. Was it possible to have a conversation with a machine and not be able to distinguish it from a human? He called this the imitation game. It was introduced in the article Computing Machinery and Intelligence. The intention was to use this test as a substitute for the deeper, more vague question, can a machine think? 70 years later, in 2020, several large language models such as OpenAI's ChatGPT passed modern and rigorous variants of this test. In 2022, OpenAI launched ChatGPT publicly and immediately captured global attention. It was the first chatbot you could have an extended conversation with on almost any topic, the first obvious application of a Turing test breaker. In 1950, many scientists thought this didn't make sense. Digital industrial revolutions. Today, the evolution of industrial revolutions is conceived as Industry 5.0 are a fundamental part of the knowledge-intensive economy. That is, an economic system where growth, value creation, and productivity are driven primarily by knowledge, information, and human capital, rather than by traditional physical assets or manual labor. Information is the main factor of this economic system. The knowledge-intensive economy was envisioned Peter Drucker in his book Post-Capitalist Society, published in 1993. Drucker argued that the basic resource of production is no longer capital or labor, but knowledge. In this economic model, the ruling classes are divided into knowledge workers and service workers. HY believes that Drucker's concept is correct, but it is not sufficient in scope, because technological evolution is dividing workers into scientists in artificial intelligence, AI users, and displaced by AI. This social change is exponentially accelerated by digital revolutions. A knowledge-intensive economy is an economic system where the production of goods and services is mainly based on activities that require a high use of intellect, data and innovation, rather than relying on natural resources or traditional physical labor. In this model, human capital and intellectual property are the most valuable assets to generate wealth and competitive advantages. Intellectual capital is the sum of all the knowledge that the knowledge-intensive economy company uses to generate wealth. With the growth of artificial intelligence, knowledge-intensive companies are now the richest in the world, and their scientists are the highest-paid professionals. The knowledge-intensive economy is born in the human brain, which is made up of a set of organs, hypothalamus, hippocampus, cerebral cortex, and others, and neurons within these organs. The production of knowledge is made up of capture of real-world information, human activity, production of knowledge, storage of information, and activation of knowledge generation. In each cycle, knowledge is produced that has been enriched through processing in the brain. As knowledge is produced, the speed of acquiring more knowledge increases exponentially. The knowledge-intensive economy is another era, in which the main technology and raw material is knowledge. The traditional thing has been that these inputs are different. Knowledge is a very exclusive technology that is only in the hands of scientists, which means that, little by little, the skilled workforce is reduced to scientists, generating a workforce in which non-scientists lose value. The machine used to produce knowledge is artificial intelligence, whose productivity grows over time. The time-discretized process must fulfill that knowledge in the period t+1 is an exponential function of knowledge in t, which means that, in the infinite period, knowledge will be infinite. This situation can result in a singularity in which humanity cannot push the knowledge it produces. By organizing the types of economy, and the dominant technologies, we have arrived at Industry 4.0. The main characteristic is that each era takes much less time to change than the previous ones. We could say that we are in a new era, Industry 5.0, dominated by artificial intelligence and the knowledge economy. It is the moment when social growth and the generation of wealth are in the hands of scientists. Digital industrial revolutions. Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. One of the most impactful changes occurs with the arrival of the Internet of Things, IoT, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models. It can be said that in Industry 6.0 all models work in real time, so that the world reacts distributed and online, for all IoT-connected systems. For static systems, the methodology is also valid, but the world is dynamic. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we can talk about orchestration of swarms of cognitive robots, and living industrial ecosystems. These two terms are new to most people, including scientists, even though they date back at least 15 years. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies. And ethical and conscious governance, AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. There are 3 eras of modern mathematics aimed at handling computers. During this period, the basic mathematics that supports optimization does not change, but the technologies do. The creation of digital computers and iterative algorithms took place during Industry 3.0, in 1947. Until the arrival of Industry 4.0, the mathematics of algorithms grew, but it was from that moment that the complexity of formulations, and the use of solutions based on advanced technologies for large-scale optimization, generated the boom of modeling. This era includes Industry 5.0. The Industry 6.0 changes the mathematical modeling, giving rise to the orchestration of swarms of cognitive robots, and living industrial ecosystems. The document, The Bender's Decomposition Algorithm, a literature review. It presents the evolution of Bender's theory up to 2016. As can be seen, the growth of parallel methods, such as Bender's partition and Lagrangian relaxation, has occurred since the Industrial Revolution 4.0. It can be said that the approach presented corresponds to a version of Industry 4.0, and that the change experienced until Industry 6.0 is very large, having affected the way of implementing mathematics, which is different from having changed mathematics. However, one of the most impactful changes occurs with the arrival of the Internet of Things, IoT, typical of Industry 4.0, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models, which are the ones that should be used today. Industry 6.0 focuses on the symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. Industry 6.0 is changing the mathematical modeling. Now we can talk about living industrial ecosystems, and orchestration of swarms of cognitive robots. This has led to the fact that, if desired, modeling in Industry 6.0 is autonomous, without human participation or coordination problems. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university, however, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. The difference between a scientific life and a real and ordinary life generate a big chasm, not a gap. The difference between Industry 6.0 versus and the previous digital revolutions generates a big chasm, not a gap. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. In Industry 4.0 there is a coordinating model of all the problems that integrate the model associated with the artificial hypothalamus. This coordinator emulates the company's board of directors using large-scale optimization methodologies, such as Bender's theory or Lagrangian relaxation. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. The Industry 6.0 approach is applicable at all levels of decision-making, from planning to real-time, uniting all entities in the system. The case of greatest interest, or utility, is related to real-time applications. Due to the Internet of Things, the amount of data that a system receives tends to be infinite. This is appropriately handled by Industry 6.0. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. The swarm of algorithms make up an artificial brain that can be solved using Industry 4.0 or Industry 6.0 models. The latter seems to be the right thing to do. Living industrial ecosystems that act autonomously, making their own decisions, and reaching agreements with other living industrial ecosystems, to ensure the optimality of the living industrial ecosystems network. The approach can be conceived as an artificial brain composed of a network of mathematical models, a model for each smart grid and for each site of large generation and/or consumption. Communication between the algorithms of mathematical problems must be asynchronous when events occur in the system. This can be continuous. For optimization purposes, the artificial brain does not need a coordinator, as the smart grid system acts autonomously and independently. However, in order to function as a technical control and regulatory control, it may be necessary to have a system supervisor. The Industry 6.0 artificial brain does not require a system supervisor. Consensus algorithms are fundamental to the operation of decentralized networks. They ensure that all network participants agree on the validity of transactions. Without consensus, there would be discrepancies in the data between different nodes, which could lead to fraud and errors. These algorithms facilitate trust between users who may not know or trust each other. Different consensus mechanisms have been developed to respond to the needs of various applications, each with its own strengths and weaknesses. In the case of mathematical programming, the rules of consensus are exact. Dispatch of an agro-industrial supply chain. Normally, an agro-industrial chain must be planned integrally, which involves coordinating many farms. IoT facilitates the knowledge of the status of each farm, in such a way that each of them can be planned autonomously and independently, following the principles of Industry 6.0. Another point of view is the spatial distribution of the problem. In this case, an artificial hypothalamus is presented for an agro-industrial company that has multiple facilities, farms, concentrated food factory, meat products factory, and stores in the food market. In Industry 4.0, for long and medium-term planning, it is possible to solve the problem using a monolithic model solved with large-scale optimization methodologies. The entire relationship between the optimization models is stored in the expert system. In real time, using an IoT system, the best solution is based on the principles of Industry 6.0, mainly on the coordination of farms, which can be many. Coordination is done using a consensus algorithm, which are mathematical rules, like Lagrange's theory, and not a coordination problem. OptEx, Optimization Expert System, is the generative artificial intelligence created by HYPOTHALAMUS that builds enterprise-wide optimization systems for global companies. An expert system, S, is a computer system designed to emulate the reasoning and decision-making ability of a human specialist in a very specific area of knowledge. It is one of the most classic and successful applications of artificial intelligence, AI, gaining great popularity between the 1970s and 1980s. Unlike traditional programs based on rigid algorithms, an expert system uses structured knowledge, rules, facts, and heuristics, to solve complex problems that would normally require years of human experience. Optex is an optimization expert system that helps the mathematical modeler and the user of the models to manage them. The result is that Optex manages mathematical models without using programmers. The image shows the structure of a traditional expert system, which incorporates a human expert, who possesses the knowledge, a computer engineer, specialized in capturing the expert's knowledge, and a user who doesn't have to be an expert on the subject. The computational architecture of the expert system integrates three parts: knowledge database, inference engine, and human interface. As an expert system for a scientific topic, such as mathematical modeling, Optex is accurate and does not require synthesizing the knowledge of experts who may differ in their opinions, which facilitates the commissioning of the system. In practice, the human expert, with computer knowledge, is a mathematical modeler, and the implementation of Optex is summarized as the intelligent management of the knowledge database. In this way, a non-expert in mathematical modeling can manage Optex, without the need to build programs. The expert system is Optex's AI approach. HY is not aware of a similar approach to mathematical modeling, and it has been used by HY since 1990. The Optex software generation involves accessing the AI expert system and processing its content, to generate the software on the selected optimization platform. Optex, Optimization Expert System, is the optimization technology that allows you to assemble multi-problem mathematical models like a Lego game. Can you imagine how? Putting problems together is much easier than writing equations. That is the future of mathematical modeling, which Optex has been experiencing for 35 years. Not writing equations is every mathematical modeler's dream. The traditional process of mathematical modeling implies that programmers, usually mathematical modelers or data scientists, must make great efforts to implement complex optimization models. Do you wonder of how to make high-complexity large-scale artificial brains, without programming? The best way to make software is haven't to do it, is the goal of Optex. The HY approach is aimed at developing cognitive robots, that eliminate the tasks of computer programming, since the robot takes care of this process. This enhances the mathematical modeling capacity of the professionals. Making an enterprise-wide optimization system, integrating multiple large-scale models, using a computer programmer, is an impossible approach, because the programmer can only write a limited number of lines of good source code per period. Maintaining these models can be more complicated than making them, if there is more than one programmer involved in the process. Only a generative artificial intelligence can produce infinite lines of perfect source code in seconds. The foundations of Optex database algebraic languages consider the algebra as a standard, to express the relationships between the different parts that make up a mathematical problem. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Additionally, if two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming, MP, which in essence is a collection of algebraic elements. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. The multiple models are assembled like a Lego game, which can have as many groups of tiles as there are models. HyPower 6.0 is the current version of HyPower, the first version of which dates to 1998. Since then, HyPower has evolved to incorporate multiple problems using a multi-problem model of economic dispatch as its core. All models that integrate HyPower have been developed using the Optex GAMS interface. using a solverplex optimization studio. The integration of the models is carried out automatically by OpTex, and the generated programs coordinate their communication through the database, using monolithic models, or in RAM memory using large-scale parallel optimization. All high-power models can run in deterministic, or stochastic, version with user-definable uncertainty dimensions. All models that integrate high power have been developed using the OpTex GAMS interface. Using a solverplex optimization studio. The integration of the models is carried out automatically by OpTex, and the generated programs coordinate their communication through the database, using monolithic models, or in RAM memory using large-scale parallel optimization. All high-power models can run in deterministic, or stochastic, version with user-definable uncertainty dimensions. Finally, it is possible to introduce new models into high power as required. Today in the Industry 6.0, the artificial hypothalamus of the wholesale market in the electricity sector does not require a coordinating model. All the models can act autonomously and independently, and the optimal solution is achieved by means of consensus rules based on the mathematics of optimization proposed by Lagrange in the 1700s. A bridge between neuroscience and artificial intelligence. Did you know that the human brain can use mechanisms like the Kalman filter to integrate sensory information and correct errors over time? Applications in neuroscience. Sensory perception. The brain combines noisy sensory signals with predictive models to build an accurate interpretation of the world. 2. Motor control. During movement, signals from the muscles and brain are corrected in real time, just as a Kalman filter would handle variations. 3. Bayesian learning. Our nervous system could adopt similar principles to update beliefs and adapt to a changing environment. These studies offer new insights into brain modeling and the creation of intelligent algorithms that simulate neural processes. Taking inspiration from nature, we can develop increasingly sophisticated technologies, from artificial intelligence to neuroprosthetics. The fascinating union between biology and technology, we can see it in eye tracking. The Kalman filter can follow a moving object, like the retina of an eye. This process requires an accurate estimation of position, speed and trajectory, even when the visual signal is altered by external factors, such as shadows or reflections. Let's imagine using the Kalman filter to model eye tracking. Prediction. The filter estimates where the object will be in the next instant, based on its current speed and position. 2. Observation. The system records the observed position of the object, potentially noisy. 3. Update. The filter combines prediction and observation to get a more accurate estimate. This same principle is used in research to understand how the brain corrects its errors when the visual signal is interrupted, for example, by blinking. The results show that the human brain tends to minimize estimation error in a way that is strikingly similar to the algorithm. Some technology applications. Neuroprosthetics, improving motor control in people with disabilities. 2. Machine vision systems, optimization of real-time object tracking to visualize results. The Kalman filter must correct the noise of the observations, getting closer to the actual trajectory of the objects in the brain. Quantum computing and artificial intelligence are two transformative technologies that, when combined, create quantum AI. This integration leverages the unique properties of quantum mechanics, such as superposition and entanglement, to enhance AI's capabilities to solve complex problems, optimize processes, and analyze massive datasets. Quantum computing operates on qubits, which can represent multiple states simultaneously, unlike classical bits that are binary, 0 or 1. This allows quantum computers to perform calculations at exponentially faster speeds, making them ideal for AI tasks such as machine learning, optimization, and data analysis. OpTex Quantum AI is the version of OpTex that produces algorithms that can be solved on quantum computers. It inherits all the AI features of OpTex Optimization Expert System. We can affirm that OpTex Quantum AI is the state-of-the-art of optimization. The reasons are: generative artificial intelligence to produce the codes of the algorithms without programmers, and access to the world's fastest algorithms. Quantum computing, unlike classical computing, is a relatively recent development. Its origins date back to the late 1970s, when it first appeared in science fiction. In 1981, Nobel laureate Richard Feynman was credited with pioneering the concept of the quantum computer. His rule of thumb was, if you can't explain it simply, you don't understand it enough. In 1985, David Deutsch formalized the concept of a quantum computer, marking an important milestone in the field of quantum computing. Having obtained the conceptual solution, HY is working on the practical implementation of OpTech's quantum AI, quantum computing and artificial intelligence. Chaining OpTechs to super server in the cloud. In this case, the current one in the industrial environment, the programs are installed on a super server and solve the problem. The generation of quantum software in OpTechs involves accessing the expert system to generate the software into a computer code according to the quantum computer, like IBM Qiskit. Chaining OpTechs to quantum servers in the cloud. This is the new approach to the industrial environment in a short time. The structure of the OpTechs expert system supports the new functions required for the new interface. HY is working in this direction considering the studies carried out for the implementation of quantum AI. This involves the generation of new computational languages and their connection with quantum algorithms. OpTechs should be installed on any computer running MS-DOS where the programs to be sent to the quantum computer are generated. OpTechs GPT is the current research and development plus innovation project, based on artificial intelligence, focused on generating a new version of the OpTechs optimization expert system, fundamentally aimed at generating a new interface, for modelers and users, of OpTechs, based on GPT-type artificial intelligence. The data source for building a model can be the description of the real model, and/or the algebraic formulation, and/or pre-existing models in the OpTechs database. The image shows the connectivity of the OpTechs and OpTechs GPT databases. The OpTechs GPT database stores different types of documents oriented to the models and solutions that the user handles. OpTechs Expert System Database, OpTechs Manuals, User Application Manuals, manuals of the work carried out for the user, and technical documents such as papers. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.